all we want to do here is to discuss the three basic facts of acceleration vectors that everyone wants us to remember. First off, remember that we're starting out with a function, r of t. We're taking the derivative, and we call it r prime of t. And there were three really good reasons why we call that the velocity vector. And remember, those three reasons are that it's tangent to the graph like a velocity vector should be, it points in the direction of motion like a velocity vector should be, and its length was actually equal to the speed with the correct units. Now, if I take the derivative of the derivative, because we're taking the derivative of the velocity vector, they're going to call this the acceleration vector. It is important to note, though, that although ordinary acceleration tells us how fast the speed is changing, the acceleration vector will tell us how fast the velocity vector is changing. But the velocity vector has direction and length. So the acceleration vector has two components to it that are very, very important. And if you took a differential geometry class, this is like exactly where you would start. Looking at the acceleration vector and thinking about how it determines how fast the speed is changing and how fast the direction is changing. So those are the two things we want about that. Finally, I want to look at that physics example we just brought up in the first case. We had started out with a circle like cosine kt I plus sine of kt j, and we saw that no matter what k was, that was a particle that was moving around the unit circle at constant speed. The way we did that is we took the velocity vector, which was the derivative of our function. We got minus k times sine of kt I plus k times cosine of kt j. And remember, just real briefly, right, if r is the vector that's pointing out like this, the velocity vector is now pointing in that direction. Now let's find the velocity vector. And since it's defined to be the derivative of the velocity vector, we can just take the derivative of each component. What I'm going to get is minus k squared cosine kt I minus k squared times sine of kt j. Now, just as the velocity vector is perpendicular to the r vector because it's the derivative, the acceleration vector should be perpendicular to the velocity vector. Now, that's a little bit weird. If we look at this one, well, and this applies to the circle stuff. What do I want here? I want to see how the original r vector compares to the acceleration vector. And you can see that the acceleration vector just has a k squared pulled out of the r vector. In other words, the acceleration vector, when you have a circle going around, when you have motion around the unit circle at constant speed, the acceleration vector looks just like the original r vector but points back in because it's got a negative there. So the acceleration vector is just going to point back in here. Now it'll be longer than r if k is bigger than 1. It'll be shorter than r if k is smaller than 1. But it's enough that if we have uniform motion around a unit circle, that the acceleration vector is perpendicular to the velocity vector and points inward towards the center. We won't be using that much in this class, but physics very much depends on it, so we had to do that.